people don't usually think about mathematics as a daring occupation.
So our first ice station, the ice broke apart and 3 of the scientists were stranded on the wrong side of this ever-widening crack. So we were very lucky that nobody was hurt.
But icebound adventure is not what draws Kenneth Golden back again and again to both the North and South polar regions. For him, it's all about crunching the numbers. The mathematician has spent the past 40 years studying sea ice. With support from the National Science Foundation, he and his team at the University of Utah are developing formulas to help scientists make more accurate predictions about how quickly sea ice will melt as our planet warms.
You wouldn't necessarily think that high-powered mathematics would be able to tell you all sorts of things about sea ice and its role in the climate system, but in fact it does. The world is becoming more quantitative, more associated with computers, mathematical algorithms. If you're going to do something in science and engineering, you have to know mathematics and how it's used and to be able to bring it to bear to your particular field.
Golden and his team use this coring device to retrieve sea ice in Antarctica.
We extract these cores and then we do electrical measurements on them.
Okay, and the resistance is 13 ohms.
We'll also take cores to do crystallographic measurements. You have different crystallographic structure based on how the ice was formed. As a result, the physical properties of the ice are somewhat different.
Sea ice is salty and has a porous microstructure which is very different from freshwater ice that forms ice sheets and glaciers on land. Understanding how seawater percolates through sea ice is a key to interpreting how climate change will play out.
We are very interested in the fluid flow properties of the ice, the snow ice formation, nutrient replenishment processes, the drainage of melt ponds. These are all very important processes for understanding the role of sea ice in the climate system, as well as ultimately understanding how polar ecosystems may respond to changes in our climate system.
And the mathematical methods developed from research in these rugged places can be applied broadly, from designing stealthier planes to practicing better medicine.
The microstructure of sea ice is very similar to the microstructure of all sorts of other composite materials. We then took those exact same methods and applied them to helping monitor osteoporosis in human bone.
Going to extremes to drill down on the role sea ice plays in a changing climate. It's well worth it. Just do the math. For Science Nation, I'm Miles O'Brien.